Today I'm going to tell you something about the methods by which we measure very small changes in length, because they have figured very prominently in delicate scientific measurements and also in precision engineering. The ability to make things precisely is one of the factors in our present technological society, and I suppose its first real impact was in the 18th century when, as you know, Britain established its lead in the Industrial Revolution, largely because of the steam engines of James Watt. Now, James Watt's engine had been a failure for several years. In fact, he almost gave up. But he met a man called Matthew Boulton, who introduced him to one of the great iron founders of Britain, a man called John Wilkinson. And John Wilkinson had already overcome the problem that had bedeviled James Watt. And this was the problem of making a cylinder which was so precise in its bore that the piston would go from one end to the other without letting the steam leak out round it or jamming if the bore was too tight. Now, that had been a great problem to solve, and it's one of those cases where military applications had benefits in peace, because Wilkinson had invented a boring machine for boring the diameters, internal diameters of cannon very precisely. And once Wilkinson made the cylinder for Watt, the Watt engine worked, and the factories and mills of Britain could be driven by steam power, giving us the great lead that we then enjoyed. As for the accuracy that was then involved, it was roughly of the order of 1/1000th of an inch. And indeed, up to World War II, an engineer who worked to a thou, as we called it, reckoned himself a precision engineer. To how many of you do the figures 303 mean anything? Yes. Or 280, or many of you will know the 45, the gun that, the Colt revolver that figured so prominently in the days of the cowboys. 45 was short for 450, and you see even a difference between 303, the British rifle of World War II and World War I, and the 300 of the American rifle was a significant enough difference to be worried about. And the .303 meant 3/10ths, no hundreds, plus 3/1000ths. And that was reckoned to be precision engineering. Today, the situation has moved on. And instead of working in thous, as we call it, those of us who are concerned work in units not of thousandths of an inch, but in millionths of a metre, or thousandths of a millimetre. These are very often, their strict name is micrometers, meaning millionths of a metre, but we normally call them microns. And I could almost entitle this lecture The World of the Micron, because it's the micron is the unit now used by engineers the world over. The Japanese, for example, engineer their railway axles to a precision of 3 microns. That's just over 1/10,000th of an inch, as one example. And to give you some idea of what a micron is like isn't very easy. But if you had a magnification of 1,000, the micron, repeated 1,000 times, would come up to 1 millimetre. And if you imagine a scale with millimetre divisions on it, which was magnified by the same amount, many of you would be between 3 and 4 feet high, or here. Well, you would grow in stature till you'd be higher even than Ben Nevis or Snowden. And it's our ability to measure to not millimetre microns, but to tenths or even hundredths of a micron, and to control our machines to turn out components to that degree of precision, which has made all the difference, and which has made these marvelous developments in microelectronics possible. It's one of those cases where the mechanical accuracy had to be achieved before the electronics could take advantage of it. And so I want to tell you something about some of the ways in which these measurements can be made, not with verniers or micrometers, which you have to use by eye, but by automatic devices where the information is effectively converted into electrical signals of a kind which can be fed into a computer. And the first method I want to talk about is one which we call the Moiré fringe method. And it started as an invention in physics by the great physicist Lord Rayleigh, who was analysing the faults that occur in a very important device in optics known as the diffraction grating, where lines have to be ruled parallel to one another and spaced very accurately over a relatively large area. And it's very difficult to see the errors in the lines, but the performance of the diffraction grating shows up the errors very prominently. And what Lord Rayleigh thought of was of making replicas and testing them one against the other. And you can't see any fault there with the naked eye, but if you take a second one of exactly the same thing, you can see that crossing it, one gets these fringes, which, because they were first observed in Moiré silk, are called Moiré fringes. And the greater the angle between the lines, the closer together are the fringes, and vice versa like that. And Lord Rayleigh was using this merely as a means of testing how straight the lines were, because any errors, as you can see over here, produces, directly I distort the grating a bit, you see those fringes at once show up a violent distortion. Well, just after World War II, Sir Thomas Merton, who was very concerned with making these kind of things, realized that here was the basis of a very good measuring system, because you see, if you move the grating one past the other like that, the fringes move vertically by a large amount for the small horizontal movement of the one grid past the other. And the closer you make the spacing, the wider apart the fringes occur, and the faster they seem to move. Well, our National Physical Laboratory developed that method, and it was taken up by the famous firm of Faraday. And here are two specimens which Faraday let me have for this lecture. As they pointed out, they're not very good. They've been used so much. But even in this rough condition, they do the job almost perfectly. And you see, now we've got a large, obvious movement horizontally for a small movement, a large movement vertically for a small movement horizontally. And you see, this is exactly the kind of signal which a photoelectric cell likes. It's only got to record the difference between light and dark, and as a result, it can send a series of pulses into the electronic amplifier every time a fringe goes past it. And with two photocells, one above the other in this plane, you can tell which way the fringes are going, either forwards or backwards, and so you can tell your calculating device to count either positively or negatively, and so you can slide along like this, and the cells can count so quickly over thousands of fringes that virtually instantaneously they can feed into the electronics the count, either to the left or the right, and so you now have automatically, and you can display it with a scale of 2 counter or a scale of 10 counter, just as you please, and you can feed the impulses into a computer, and if that computer has already been programmed so that it knows the kind of pulses that it wants for the cursory devices, we call it, to move to, and the first lantern slide would show the the first one, that one, you see. There is the diagram where the long scale is attached to a machine tool, and the smaller piece of grating with the fringes on it is attached to whatever it is you're wanting to move, usually a cutting tool, along the scale, and you'll have another scale at right angles to that to tell you where it is to the right or left of that picture. So you can, and also up and down if you wish it, so you can position the cutting tool in 3 dimensions, and so you can program the computer to tell the cutting tool where it ought to move in order to machine very complex shapes indeed, and the operator, having set everything, has merely just to watch and see that nothing goes wrong. And this system of Moiré fringe measurement, perfected by Ferrantes, is now in widespread use throughout the world. An alternative method, which is I would say of equal importance, depends on our old scale of 2, and it works in rather a different way. So if we can have the next slide, we could take, if we liked, an ordinary ruler to start with, and taking its finest divisions, we make a transparent ruler to start with, and and we take the finest divisions and we black in the alternate ones. And we duplicate that ruler down here by as many times as we please. And in the second channel, we black in alternate 2s. In the next channel, alternate 4s. Next channel, alternate 8s, alternate 16s, and so forth, to as many powers of 2 as you wish. And then you attach that to the base of the machine on which you're measuring, and on the moving member, you have a line of little photoelectric detectors, each one of which looks through that part of the scale. And you then ask the photocells one simple question: can you see light? And all you need to know is yes or no. In this position, cell number 1 says yes, because light can come through the transparent scale onto it. Cell number 2 says yes. Cell number 3 says no. Cell number 4 says no. Cell number 5 says yes. So we got the sequence yes, yes, no, no, yes. And nowhere else on that scale will you get that sequence of answers. The nearest you'll come to it, perhaps, is the corresponding one over here, where we've got no, yes, yes, no, no, just as we had there. But now, here, we've got no instead of yes. So we know it's in that position and not in this position. Of course, if we wanted to do longer scales, and we had this again, this would repeat another 16 further on. And that is why in the next scale, we have to black in this 16, and so forth, you see. But already, with only 5 of these, we have uniquely found one position in 32, and with 10 of them, we can find any one position in 1024. And of course, these are, again, exactly the kind of signals that photocells and electronics and computers like, simply either yes or no. And indeed, you can imagine the scale of the two counters working from these in a rather similar manner to the elementary one we worked with in our first lecture. Again, it is this mysterious, almost mysterious power of the scale of 2. And in case you think this might just be, as it were, an academic illustration, let me show you the next slide, which the Decca Company have let me have, which, if you look along here, there is almost what we've shown on the previous slide. And that is part of the pilot's map, working from the very impressive Decca system of radio navigation, where the radio receiver tells the pilot where he is by the position in the pattern which the Decca transmitters set up. And so as the pilot is flying along, this map moves up before him, and also as he moves right or left, the index mark could move there. So more or less at any time, he can see where he is. Now, how does the map know where to set itself? And the answer is that its position is monitored by little photocells working on this increasing scale of 2. And so the information from the radio navigational system is converted into pulses which can be compared with where this should be, or at anyone across there. And so the map can be automatically adjusted by comparison between the reading off here and the reading coming from the radio instruments, and when they are identical, then the map is in the right position, and of course they'll be changing all the time, and so the map will be moved continuously. So there are 2 methods of automatic reading of scales. Of course, you can't do very much better, and we've seen you can do better, but not all that much better than the smallest division on here, or the smallest fringe separation in the Ferranti system, but that is still good enough to get us automatic readings down to something of the order of a micron. And that means really very precise control for machine tools. So we have these 2 optical methods, and we have yet a third one, which depends on the fact that light is a wave motion. And for that, I would like to show you some patterns on the overhead projector which may enable you to understand what is happening rather more easily. And this is a very famous demonstration developed by Professor Pohl, who was a great demonstrator of physics principles in the University of Göttingen, and after the war, he let me have 2 of his plates. And here you see we have something that simulates light waves, ripples going out from a source like that. And if you've got 2 sources with a similar plate like that, you can demonstrate the kind of interference because you can see where the waves are reinforcing, where the light is, and where they're interfering with one another, where it's complete black. And you will see the pattern, just as in Thomas Young's famous experiment done in this institution just after 1800, showing the interference of light from 2 slits, like that. And in the thing that I'm going to show here in a moment, the interference is just rather the other way round. Let us put them that. I want to get the 2 sources lined up. That's better. Now we've got them completely lined up. And I'll move the one source, not now sideways with respect to the other, but either ahead of it. So we start there, and we see now successive fringes coming like that. Now, if you look at that pattern, like that, and the 2 sources are one behind the other, you will see that there are dark bands. And we're going to create 2 sources, one behind the other, by shining a laser, and the next slide will show the diagram like this. We have light from a laser, which we're spreading intentionally. It normally is very parallel, but we're making it spread as far as we can. And light from the laser strikes the piece of, in this case, mica, but it could be glass, any transparent subject, material, and you see it comes away like that, and it looks as though it's come from a source here. But also, some of the light, most of the light, doesn't go, it's reflected, it comes through. And it comes through like this, refracted here, comes back, bent back again, parallel to what it was, but now it looks, that lot of light, looks as though it comes not from there, but from there. And so we have 2 sources now, one behind the other, as in the pattern on the overhead projector. And so at some angles here, there will be darkness, at other angles, light. Now you've got to remember that we're not working just in a single plane, but we've got the whole available, with the result that if it was dark at this angle here, it's also dark at the same angle there. And in fact, there will be a circle of darkness out here, surrounded by a circle of brightness, another circle of darkness, and so forth. And if we can have the laser on, and we can drop the lights a little, we can what shall we do first of all? First of all, I ought to show you, didn't I, that if it is an ordinary piece of a single surface, one gets nothing, I think it is, yes. If it's a single surface, one virtually gets, there's a mirror there, one's just got light spread. There are some imperfections in the pattern. I don't know whether it's worth showing you. Yes, it is, I think, isn't it? This shows you an very important fact, incidentally, that this is the shadow of a needle, you see, in the laser light, and you can see the eye of the needle. And later I should be saying what does limit us in the precision of our measurements. And one of the things that limits us is indeed the fact that light is not of infinitely short wavelength, and that whenever you look at an object, light is bent round it and diffracted, and these bands, which you can see to the side of the needle, or indeed right down the middle of the eye, are due to the diffraction of light, and if you're trying to measure very accurately the diameter of the needle with a microscope, you will find that this phenomenon limits the precision with which you can establish the edge. But that is quite incidental to what I want to show you as the main thing. Remember that we're predicting, we hope, that a series of light and dark fringes caused by the... Now I've got to turn the main mirror. In fact, it can come down there like that. Now we've got a series of light and dark fringes corresponding to the interference between the two sources. You've got one behind the other in this direction, and as we see from the diagram, there are some directions in which the light from the one interferes and other directions in which it reinforces, giving these things, which a characteristic you see, you didn't get it with a single surface. You must have the two surfaces, one behind the other, and we get these rings that you can see. And the BBC cameramen and engineers have managed to store this picture. And can I know when the storage is all right? Because what we want to do is to try to show you that the wavelength of blue light is different, in fact shorter, than that of green light. And Mr. Coates will now change the tuning of the laser so that blue light will come up on the screen like that, and we get the interference pattern in blue light. And that's stored all right, is it? And now, if the engineers will kindly switch from the one to the other, you can see that the pattern, the rings are separated differently in the green from the blue. And this is, if you go into the physics of it, this is because the wavelength of the blue is less than the wavelength of the green. And thanks to the BBC cameramen engineers, this is, ladies and gentlemen, the best illustration I've ever seen of the difference in wavelengths of these two colours, or of any other colours. Now, that fact enables us to realize the more than century-old dream of physicists that we might be able to relate lengths not to some mechanical or material standard that might perish in a disaster, which would survive even the destruction of the whole Earth. Because the wavelength of light, we've seen, of course, it changes from one color to another, but if you can specify the atom from which the light is being emitted very precisely, and it's not precise enough just to say which element you want. You've got to say which isotope of that element you want. And the one which has been found most convenient is the atom of krypton with the atomic weight of 86. And from 1960 onwards, and this is one of the side shoots, real benefits of atomic energy developments, when single isotopes could be isolated, it was possible to make a lamp emitting light of such purity that there would be no doubt about its wavelength. And from that time onwards, the metre, which had originally been defined, you see, as 1/10,000,000th of the Earth's quadrant, as we saw, it was a very impractical unit, now, from 1960 onwards, defined in terms of the wavelength of the orange light coming out of the krypton gas when it was under very precisely controlled positions as 1,650,763.73 wavelengths, and that is now the standard. And techniques are already advanced to the stage where almost at any time an extra figure of precision might be added to that definition. So now we have an absolute way of referring to measurements of length. And it isn't all that difficult to do, fortunately. Again, thanks to the availability of single wavelength lamps, in other words, lasers, and the ability to count the fringes as a mirror moves. I only showed you with one separation there, but if we put a thicker piece of glass in, we'd have found a different separation for the fringes. It is possible now to make very precise measuring instruments where the measurements in all three dimensions, X, Y, and Z, are all made by means of lasers and a fringe counting device. So one can, in fact, work directly, not off material standards, but off light waves, if you want to make the most precise components. Well, all this, of course, has resulted from a tremendous amount of painstaking work, but there is an old method which is even more sensitive when it comes to measuring very small displacements. And it started early in the 19th century, but was brought to, as it were, being one of the principal methods, and certainly of enormous value in physics, by Lord Kelvin, whose portrait is on the next slide. Now, Lord Kelvin was not only a very fine physicist, he was also a very fine engineer. And one of his greatest jobs was to set up the first Atlantic cable. And he knew he had a problem. The problem was that 3,000 miles of cable, 3,000 miles back, it had to have inevitably a large resistance. The biggest battery you could put across it to drive a current through it was limited by the thickness of the insulation you could put around it. And putting on the biggest battery he could and using the most sensitive instrument at the other end, he wasn't at all sure that his galvanometer at the other end would register easily enough for an ordinary operator to be able to see whether it was flicking this way or that way, and whether it went that way or that way was an indication, of course, of signals with the Morse code. And the story is that when he was pondering this question, he'd happened to notice something that so many of us have played with, at least in our younger days. You know, if you get a mirror and you can get the sun playing onto a wall in shadow, you can have a great game with your friends trying to get, they try to catch the reflected spot on the wall, but by the time they've got their hand there, you very easily, by a small movement of the mirror, have flicked off the image to where it's somewhere else. The story is that Lord Kelvin, perhaps he didn't do that in his youth. He went to university too early. He was only 12 when he went to university. But anyway, in his older days, he wore a monocle. And the story is when he was worried about this problem, how could he make the reading of the instrument more obvious? He saw the light from his monocle reflected, at least the reflected image of the sun, from dancing on his laboratory wall. And he thought, that's it. And so he attached a mirror to the suspension. And the combination of the mirror and this kind of device, which had been invented in around 1750, 1760 by John Mitchell in Cambridge, made a very sensitive instrument. It consists quite simply of a thread or strip, and on it you put whatever is the system, usually in the case of Kelvin, a galvanometer coil here, so that when current passed through it, the magnetic field around it, it would deflect sideways. And instead of putting a needle on, you see, and a scale out there, he put a mirror on, shone light onto the mirror, and shone it off onto a scale, which could be as far away as he pleased. And now he had a lever, you see, with virtually no weight, and which could have a very great length, because light traveling virtually in straight lines meant that you could go as far as you pleased. And because it was an optical device and it was a lever, he called it the optical lever. and it has been at the basis of many of the most important measurements in classical physics. Now, more recently, it's had other applications, and we will first of all demonstrate the fact that if you have a source of sound, in other words, this loudspeaker, in this case, and there is a diaphragm near it, in this case the diaphragm is stretched simply across the mouth of the loudspeaker, the diaphragm is set into motion by the sound waves striking it, and indeed these will show up very simply. First of all, you can see the little bits of mirror which have been stuck on the diaphragm, and we will watch their behavior as the laser comes on, and there is, from this particular mirror, there is the spot of light, like that. Now we will set the loudspeaker going, and well, thanks very much. You see, well now, what I want to show you now is a development of that, which you may well have read about. I'm not sure whether James Bond used one, but certainly it's one of the favorite weapons in current espionage stories. And that is what we call the laser eavesdropper, a device by which it is possible, under good conditions, to hear what is going on in a room when you've not been able to put a microphone inside it. And so you've got to work entirely from outside. And this diagram will give you an idea of what it is. There we have a laser pointing in the direction of that little house, and it goes through the window. You can work off the window, but it's better to go inside. And here is a picture frame. And much exaggerated, the picture frame will vibrate like that, in sympathy with any vibrations that fall on it from people talking in the room. If you can pick up a reflection off the glass of the picture frame, as it bends like that, it will move the beam coming back. And we now have an optical lever equal in length from there right across to there, and it will swing about. It's a tiny amount, of course, less than a micron, certainly, here, from one photocell to the other, and that will generate currents of the same frequency as the vibration in the picture frame. And so now, if we switch on we'll pretend here that there's a radio going in the house, and we will listen to now you'll just be able to, if you're near, to hear this, but now okay. Yes. Actually, I think we're listening to New Zealand. And all that sound is coming along the beam of light. Must let him do that bit again, mustn't we? Yes. Yeah. Well, that's how to make a laser eavesdropper, provided that, of course, you wouldn't use light that your victim could see. You'd use infrareds so that he wouldn't be able to see the light beam very easily, but it shows one's got to be careful. And with these techniques, properly applied for scientific purposes, very small movements can be detected indeed. But I would like to show you another method which is entirely electrical, depending on a change in capacitance between two plates. I have done something with my stick. I think, can we have that diagram up there? Because we can have a slide up too, which will show the device. I'll use this for the moment because in the case here, we have a mild steel bar, and attached to the mild steel bar is this unit. The vital part of the unit is, or the two plates here and here, one of which is positioned by the framework. It is connected right up to here. The other one is positioned by this probe, which is flexible. It can move in and out, and if it moves in or out, it changes the distance between these two plates. Now, imagine that turned upwards like that and attached to the bar. And we then have this situation that if the bar were perfectly straight, it would be resting on these points above the plate underneath. And one of the two plates would be in contact with the base. The upper of the two plates would be in contact with this and therefore the rest of the bar. If the bar or the beam bends, for example, it bends upwards, it lifts that plate relative to that distance increases and the capacitance decreases. And these changes can be sensed electronically. And what we will try to do is to show you what happens. And we'll adjust the instrument. Now, you'll see as the light goes down, look what happens. And if we can have the lights up again. So could we bring the lights up? So it's all right, it's all right. It's coming across. And we'll drop the lights again. And let's have them once more up. And you see, this is an entirely different meaning to the phrase bending the beam, because that is exactly what the lights are doing. Because when the lights are on, the extra light falls on the top of the skin of this mild steel beam. And you know, when things are heated, they want to expand. Well, the top of the beam wants to expand. The bottom of the beam wants, if possible, to stay as it is because it's not been heated. And the only way in which that conflict can be resolved is by the beam bending like that, so that the length along the outside perimeter is greater than that inside by the amount of the expansion. And so when the skin increases in length, it tries to stretch the top of the beam, and that is the effect that you were seeing there. The total movement, of course, is quite small. It's certainly less than 1/1000 of a centimetre In other words, less than 1,000th of a micron, well, less than 100th of a micron, but in typical cases, it's less than 1,000th of a micron, the movement here. And if I were to tell you that that is the apparatus throttled right back, that we have 1,000 times as much sensitivity as that, if we could show it here, you can see how sensitive this method could be. Now, in a quiet laboratory, you can see things, of course, which otherwise would be undetectable because so many other effects would be going on at the same time. But I'll tell you a little about one of the applications, one of the most entertaining applications we made of this device. And that was to build what we call a tilt meter, and I think we could have the other diagram up. If I could have the next slide now. This little instrument here, when I say little, it really is quite small. It's under that cover here, and if the diagram is up, I can explain. It is an electronic plumb line. The plumb line is only this little piece of metal here, about 3 centimeters high, which is hanging from the framework, and on either side of it is a plate. And the situation is like this, that if the instrument is set up initially, one tries to set it so that this little piece of metal here is hanging symmetrically between these two plates. But supposing that, for some reason or other, the Earth changes its shape and it bends so that the instrument is now sitting on ground like that, the plumb line still tries to point towards what it assesses as the center of the Earth, but the whole instrument is tilted, and so this plate moves nearer to the hanging one, and this one moves further away. And just as we had with the Wheatstone bridge, but now with capacitances, we have originally capacitances, both of which were equal. Now, indeed, they're quite different. And that difference can be made to indicate the change in level. And the vital part of the instrument is only this, which is about 6 centimeters high. All the rest of it is the device for leveling it up in the first place. Now, when we did this for the first time, I was thinking we would detect the difference in the pull of gravity due to the sun and moon moving about. And indeed, we can do it. But I found there were much bigger effects coming in. And for a few days, they were very puzzling. When we took a record, if we could have the next slide, these were 4 continuous days of recording. We've got to imagine that goes on to there, that goes on to there, and so forth. But starting at the same time every day as we split them up here. And the first thing we saw was this beautifully regular pattern like that. There were also things happening at about 8 o'clock in the morning, which turned out to be the porter coming into the room and his weight bending the 2-foot concrete floor. There were smudges like this, which turned out to be the movement of the ground caused by earthquakes, even as far away as the Pacific. But in addition, there was this much more challenging rhythmic thing happening approximately twice a day. And it turned out very quickly that this correlated with the height of the water in the North Sea. And at high tides, our instrument in our laboratory and the whole of Aberdeen was bending eastwards. Now, this is rather hard to believe because Aberdeen is famous as being on granite, and even the granite was being bent. And it must be the weight of water in the North Sea. And when you're working at these orders of dimensions, one of the best pieces of advice you can have is to forget don't believe that anything is rigid. You've got to think of even the strongest steel as something like jelly. And that goes even for granite too. And here, you see, is a jelly. And that is the surface of the Earth. And if we increase the local loading as the extra water in the North Sea at high tide, what happens is, you see, it sinks down, there's a compression, and the Earth doesn't crack, fortunately, very often, but it has to bend inwards like that towards the main areas being depressed. So the whole of the east coast, we haven't measured it other than around Aberdeen, but it must happen everywhere, tilts over in the direction of the sea every time the extra water comes in. And, oh, there was sinking an oil well with any luck. Well, and that turned out to be the explanation, and we found the effect was biggest when there were spring tides and smallest when there were neap tides. And this somehow appealed to the popular imagination when we discovered it, so much so that the news of it went round the world. It even appeared in a headline in Australia as a tilt in the kilt. And among the pieces of correspondence I received was this one from someone of your present age. At school, for science, our teacher said that Aberdeen slants when the tide comes in. Our class does not believe this, but if it is true, we would like some information about why this happens. We hope it isn't too much trouble, because all of us are very interested in finding out more about it. Yours sincerely, and please write back. Well, I did write back, of course, and as a result, I got the next letter. It says, "Thank you very much for sending me the diagrams and explanation of Aberdeen. It was very good of you to take the time. Yours faithfully, Eleanor Wallace." And you see, research sometimes has some quite unexpected rewards. Now, Miss Wallace must be around 24 or 25 by now, and if by any chance she sees the program when it goes on television, I'd like to tell her I'm ready to collect payment any time. Well, we can use these instruments to measure tilts. They might even be of value. Some of them, for example, on Etna, in one or two volcanoes at the present time, because when a volcano is about to erupt, it very often rises rather like a cake, and you can see sometimes the imminence of, but not always, unfortunately, an eruption by the swelling up of the volcano. And these instruments may have an application in that direction. But seeing the sensitivities that we can achieve, one naturally begins to ask the questions, are there limits to what we can do? And we come back fairly quickly now with the answer, yes, there are limits. And one of them is set by the fact that everything undergoes Brownian movement. I won't say much about Brownian movement because I think Professor Rogers talked about it at some length 2 discourses ago, and some of you may well have been present. But the simple fact is that everything is in movement due to the thermal vibrations of the atoms and molecules, and even something which at first sight is not a molecule, it's something much bigger, that too, these suspensions are in movement all the time, if we could see it, because they're being kicked about like a football in a shower of peas. And indeed, in some measurements I made a long time ago now, one could see that if the mirror was fixed with one of these optical levers, one got a beautifully straight record with time. But if you let the mirror swing freely, depending on the amount of damping you had on it, it's kicked all over the place like that. This was a very small amount. It was only 1/10 of a micron at a metre, but you can see it's very easily detectable. And you see it limits the accuracy with where you can say the zero really is. The longer you go on, the more accurately you can establish the true average through the random noise, once again indicating that accuracy costs time. And only by going to absolute zero, which is impossible, could we get rid of that disturbance. And you've got to think of all your measuring machines, all the tools, all the rulers, they're all, if you could look at them in a great enough magnification, you'd find there was always this uncertainty. But even if you got rid of that, there's another one. Even if you shone light onto the thing to read it, at first sight that seems innocent enough, but in practice it will give you an uncertainty. And for that, if we can have the next slide, I will try to show you that light really does exert a mechanical pressure. And the apparatus is on the table here. The beam from the laser fires through onto a mirror, very much like the one, much reduced in size, of course, the one there, which is free to turn on a fiber at right angles to here like that. And the light bounces off the mirror, and to get more out of the system, we actually throw the light back on the mirror again, bounce it backwards and forwards several times to build up the pressure in the light, while at the same time the mirror on the other side of the suspension acts as the optical lever pivot and throws its light across here onto that screen there, which is the green screen you can see. And what I will do is to cut off the light, and I could get a bigger effect than this, I think, with any luck. Now, the temperatures vary so much that let me just see if I can get a bigger effect. See if that's, I think I can make it bigger still with any luck. Yes, I know what I want to do. I want to do it like that. Now, let's see whether we can make it obvious to everybody. Here we are. You see? And without any electronics, just simply mechanics and optics, and building up using the principle of resonance, like on a swing, one can set that suspension swinging really from one end of the scale to the other, like that. And you can now say that you really have seen light, just the momentum of light, moving an object which you can actually see. And so whenever you look at a ruler or anything else, I'm sure your teachers wouldn't take this as an excuse for bad measurements, but nevertheless, in the limit, it is true. And although it's a very small effect here, it's very important in nature because it is the force that keeps the stars blown up to the size they are. It's the pressure of the radiation coming through from inside that, against the force of gravity, that keeps the stars the size they are. And if their nuclear furnaces die down, the radiation can no longer support them, they collapse and explode. Well, that's all I can tell you for today. And in our next lecture, we will look at the other extreme. We've been looking at very small measurements today. Next lecture, I will talk about how we make very large measurements and something about how they enable us to see where we fit into the whole pattern of time and space. Thank you.